So our speaker today is Professor Zhang from Shanghai, who will talk about getting more solutions from solitons, a limit approach.
Good morning, everybody. I'm from Shanghai University, China. This talk is a joint work with Professor Hidden. I'm very happy to be here, and this is a very nice place for scientific research. I thank the institute and the organizers and you all for participation. Okay. So my talk is getting more solutions from solitons. I will introduce a limit approach and how to get more solutions from solitons. So in continuous case, we have, I'm glad to use sticks. In continuous case, we have several methods for finding solutions, and all these methods are well developed, such as inverse scaling transform, Riemann-Hilbert method, and Da-jun transformation, and Backlund transformation, Sato theory, and bilinear method, including Hirta's method and the Wronski approach. For solutions, we can get solitons. And also we can get other solutions, for example, the postons and regional solutions. So one question is how these solutions are related to each other. Maybe they can have some relation by taking some limit. For discrete systems, we also have solving methods such as Cauchy matrix method and Sato theory bilinear and double transformation inverse scaling transform. The inverse scaling transform is very earlier, maybe in 1975 or 6, given by Ablois and Ladik. The Cauchy matrix method is related to, okay, this is a method for continuous systems, and this is for discrete case. And the Cauchy matrix method is related to somehow to inverse scaling transform by Cauchy matrix. And the difference is in the inverse scaling transform in IST, the Cauchy matrix is an expression for n solitons, and in Cauchy matrix approach, and it is a starting point. And double transformation and double transformation for both cases. In continuous case, we have Wronski for n-soliton solution, for expression for multi-soliton solutions, and in discrete case, it is Catheridi. Yeah.
You said Ablois and Ladik.
Yes.
That made me think about differential difference.
No. He has two. Yes. He has.
Two different.
Yes. He has two papers on. Yes. And the paper is published on applied mathematics. Sorry. So, my talk will consist of 3 parts, and first we will discuss some solutions in continuous case, and then we will look at solution structure and relations in terms of Wronski, and finally discrete case. So now the first part, Euro solution and limit solutions. What is limit solution? So I would say this is an example rather than definition. And, for example, in continuous case, for nonlinear evolution equation, we can have multi-solitons or n-solitons. And usually, these solitons is identified by amplitude and velocity, and in other words, is related by to some parameters. And for example, for the KdV equation, we have one parameter for both for amplitude and velocity, and for nonlinear Schrödinger equation, we have different parameters, and one is for amplitude and another is for velocity. So in general, the solitons is identified by distinct parameters, and this is an example in traveling wave form. If we take, for example, K2 go to K1, C2 going to C1, and we can get limit solution. So this is an example of limit solution. For limit solutions, there have been many examples. And one earlier example is rational solution for the Kp equation, Kp1 and Kp2. But for Kp1, we can get lump solution. And another example is resonance of line solitons of Kp2. It is also a kind of limit. The double pole solution in Hilbert form for modified KdV, and the rational solution in Wronski form for KdV, and also Riemann-Hilbert form method for multiple solutions, and the inverse scaling transform for multiple solutions. And many other examples, many examples. I will introduce some of them in continuous case. I hope they always work in discrete case. Will work, not always, sorry. So the first example is inverse scaling transform for getting multiple solution, multiple pole solution for the modified KdV equation. So this is modified KdV, and a solution expressed through K1, and K1 is a solution of PRM integral equation. F is some contour integral, and we can calculate the residue and calculate the integral by calculating the residue. So if, in general, for solitons, in reflectionless case, and the simple pole, and the residue is very easy to get, and we can get normal solitons. But we can also get if the pole is a double case. In fact, how to calculate the residue is right. To calculate this residue, it is a procedure of somehow limit. So that means the double pole solution and the simple pole solution will be related by some limit procedure, and the result is also so. Sorry. And the solution is some limits of breather is some limit of two solitons. This is for modified KdV equation. The second example is Hilbert method for double pole solution, and also for the example is modified KdV, and this is bilinear modified KdV. And to get solitons, we take Hilbert's perturbative expansion like this, and F1 is in the special form, is a linear summation of exponential, and then n solitons is very clean form, explicit form. So in double pole case, the change is here. Solitons, the parameter is some constant or 1, and in double pole case, we add here a linear function of x and t. So in this case, we can get double pole solution, and for general end, the expression is also clear. Now, we have two expressions for general n. I mean, one is solitons, and one is double pole solutions. They are related by some limit procedure. We can do that, but we don't do that now here, because it's just a trivial mathematical procedures. Next example is double transformation for the KdV equation. And this is KdV Lux pair and n solitons in Wronski form. Phi j is a solution of Lux pair with spectral parameters lambda g and zero potential. How to get some generalized solution, or how to generalize the double transformation procedure? We need auxiliary equations besides Lux pair. And the auxiliary equations is for psi, and also there is a phi here. So the first step to get generalized solution is same as the normal double transformation. But in the second step, we introduce psi here and here, and we get solution is expressed in terms of Wronski with entries phi and psi. Now this may be clear. It may be a clear form if we take zero potential case, and this is solution, and phi and psi are determined by these four equations. So now we can see how they are related. The first is just Lux pair with zero potential, and the second is a derivative of first two with respect to k. So psi is some derivative of phi. In 1991, Matveyev gave a generalized solution in generalized Wronski form for KdV, and he got positons. And the positon means in Lux pair in the stationary linear Schrödinger equation, the lambda g is a positive, and if it is negative, and we can get solitons, and in this case we call it higher order negtons. And in fact, this kind of solution is can be considered limit solution. And how to get it in a limit way? We can rewrite the solution in fraction form, and we do some Taylor expansion for phi 2, phi 3, phi n at the point k, k1, and then take limit, first limit, and we get phi 1, and here is not phi 2 instead, but phi a derivative of phi 1 with respect to k1. If we repeat such procedure, then we can get solutions given by Matveyev. This is generalized Wronski solution, and it is limit solution. Now we have seen some examples on limit solution or on the generalization of solving method in continuous case. And some solutions we get for example, the double pole solution or multiple pole solution is a kind of limit solution. The next question is what kind of solution we can have? Or in other words, what's the solution structure or how they are related together? We will take Wronski as an example, or we will discuss such questions in terms of Wronski. Why we use Wronski? And one thing is in the level of n-solitons, and we can have several expressions and Cauchy matrix, and here it has exponential polynomial form, and they are, and also Wronski form for n-solitons. They are related together by some factor. We can take some factor out. And also the Wronski is in a very regular form in continuous case, and the second column is the derivative of first column, and then the second derivative, second order derivative. Such regular form, maybe it's easy for us to consider limit. One thing I want to mention here, if we pardon? X, yes. X. Yes, because, yes. Roughly we have, for example, we have two variables. One is X and one is T. So the column is derivatives with respect to X. I can understand your question. Yes. So the difference is here phi is a function, not here. 1. And here phi is a function in our entries in the entry vectors. And for Wronski, we can write phi, and the first column is phi, the second column is yes, phi x, and in this case. But, yes, okay. Yes. But here, for example, here is phi 1, phi 2, phi n, and phi 1x, phi 2x. In this case, we don't need phi 2, or we can take phi 2 is yes. Yes. We only need one function. Yes, and phi 3 is a second order derivative. It is a Wronski because now we use new phi. We can take. Yes. But now in this case, the vector is square second order. Sorry. 1, 1, 1. Third order by 1. No. For this one, yes.
So in a limit case, you have such vectors.
Yes.
Whereas in the general case, which you were just doing, you have every entry in the vector is different.
Yes.
The vector case, the Wronskian is the determinant of fundamental solution. Is not this?
Yeah. Yes, we can. Yes, we can say that fundamental solution is solitons, or just with different phi 1, phi 2, and phi n. Okay, so we take KdV equation as an example for the structures in Wronski. And this is KdV and transformation and bilinear form. And n solitons for bilinear KdV, it is Wronski, and we use this shorthand expression. And the entry factor we need have to satisfy such conditions, which we call Wronski conditions. And now phi is a vector field. So we just consider some general phi, and in fact we don't know, for this moment, we don't know what phi is. We will try to find what phi can satisfy such conditions. Gamma here is a coefficient matrix. If gamma is a diagonal, and we can get n solitons. This has been proved in the first paper of Wronski technique by Freeman and Nemo. And gamma can also be a general form, a general matrix, which means it can also be another form which is different, not diagonal. And this is given by 1988 and from Australia, 3 people. And this is the first one. It's a very long name. Sorry. Another thing is gamma and any of its similar form lead to same solution to the KdV equation. The reason is the reason of this point, of this claim, is if now we have conditions phi x equal to gamma phi and okay, double x. And if omega is similar is a similar form to gamma, and then this will be because gamma is a constant matrix phi omega A, or maybe in this way. Yeah. And then we can take a new factor for psi, which is A times phi multiplied by A left XX. So from this condition, we get such condition. But phi and psi are related by and in Wronski, we just have f psi equals to a determinant times phi. So these are relations. And we have a transformation U equals to in this transformation, this coefficient can be cancelled. It doesn't contribute anything, so that means phi and psi give same solutions for the KdV equation. Or in other words, we only need to consider the canonical form or some special forms of gamma in terms of same eigenvalues structure. Some examples is if gamma is a diagonal and we have solution for phi, or somebody call it negligence because the lambda is is negative. And in this case, if we take a j plus and plus minus in this way, and we can get n solitons in Kirchhoff's form. So, not in Wronski, a solution given in Wronski form is not very strict, very direct.
If you multiply from the right, of course you receive the same solution.
Yes.
If you multiply from the left, it's a gauge transformation, and gauge transformation usually change position of solitons. I don't understand what you're talking. You know, in linear differential equation, you can multiply fundamental solution from the right.
Yes.
You cannot multiply fundamental solution from the left.
But you multiply from the right.
No.
Psi with a psi.
Huh?
The reason is
Fundamental solution can be multiplied by a matrix from the right.
no. In this case, no. This is gamma is similar to omega, and so now it's minus and omega and a phi, and we can move it here.
No, that I understand.
Okay. So
That's how we do multiply.
it's yes. Sometimes there is another trick, but maybe I will talk about it later. And if gamma is a diagonal, is a Jordan block case, and we can get limit solution. And for such coefficient matrix, we can have a general solution for this equation. And the general solution is expressed through the derivatives, and here A and B are Toeplitz matrix. Lower triangular Toeplitz matrix, and means, and here they are same, and here they are same. The lower triangular Toeplitz matrix is in this case is a very useful form for the expression of Jordan block solutions. And we can also see it is all the such matrix can form a semi-abelian group with identity, and yes, okay, I can give you an example for your question.
What means semi-abelian with identity? Can be without identity?
No, okay, so the unity is also a kind of lower triangular Toeplitz matrix. And this is 1, and all these are 0. So this is unit. This is unit, our identity in the group. The abelian means if A and B are two such kind of matrix, and they can commute. Oh, sorry. They can commute.
Want to be semi-group rather than semi-abelian?
No, I think this is about mutation. The solution.
Okay. If we series gamma and phi, if gamma is also a such kind of solution, I mean, in general case, for example, the Jordan block, it is in this form. It is a Toeplitz matrix in lower triangular form, and this is also a lower triangular Toeplitz matrix, and then we can left multiply, but they can exchange, switch. So now we get some, I mean, in this case, A phi is also a solution. Yes, because they commute. So in this way, we can get more solutions, and this is why we use.
I still don't understand. What is semi-abelian? I know what is abelian, what is non-abelian. What is semi-abelian?
Okay. In the group, we can we always hope, yes, we need every element is inverse.
You mean an abelian semigroup?
Yeah.
Not a semi-abelian. Yes.
Oh, sorry.
Semi-group.
Yeah, semigroup, sorry. No, not semi, okay. Yes. Here, change, yeah, okay. Semigroup, okay. Semigroup with identity, and the elements in the group is can commute to each other, okay. Sorry about that. For the Jordan block solution can be derived, obtained by some limit procedure. So this is solid. This is a Wronski with different phi 1, phi 2, and we can take some limits and get derivatives. And in this way, Wj is also a solution of binary equation. So in the level of binary equation, the limit is okay. And the way to do that is we can do some gauge transformation for the binary equations, and then we take limits, and then we can get here is get a Wronski. Here is a derivative with respect to rho. And the other is phi 3, phi 2, phi n. So the conclusion is we can make use of lower triangular Toeplitz matrix to get some simple expression for Jordan block solutions. And solutions in Wronski form, we only need to consider two kinds of form, a diagonal or Jordan block. And they are related by some limit procedures. And so we can say solution in Wronski form, just Euro solution and limit solution. The limit solution procedure is very strict and explicit. I mean, even the such matrix can be derived in the limit approach by taking the coefficients dg is some function of k. So this it means once we get n solitons, it is possible to get some generalized solution. For example, the limit solution. And in Wronski case, it is easy to do that. Just take some derivatives and add coefficients of lower triangular Toy-Place matrix. So this is solutions in Wronski form. And in Satow's theory, solutions can also be given in Wronski form. And in that case, the Wronski condition is such kind of equations without any coefficient here. So it's easy. I mean, this is a free limit if we take derivatives. You can do it, and the equation is also right. So for Kp equation, we can take we can have free choice for Wronski entries, but the relations between the solutions for me are not clear.
Could you highlight the first line, the high-dimensional bilinear equations, local relations? What
The Wronski in Satow's theory, Kp equation can be expressed in bilinear form. And this is a political relation. Yeah. It's a kind of Laplace expansion. In the book of Da-jun Zhang, they give several examples to calculate to calculate the Wronski entries, not Wronski entry, to calculate tau function starting from some element of transformation group. But I don't know the relation between our what kind of element, and we can get rational solution or solitons. Maybe Professor Noy you know that. For dynamics, and the linear solution have a very common feature. The asymptotic behavior is a kind of logarithm curves. This is a nonlinear Schrödinger equation, two solitons, not total, limit solution. And this is KdV, and here it is singularity, and for this line, singularity, and this is normal solitons, and these are also logarithm curves. This is limit breathers. So now we can go to discrete case. We have to recall some notations given in Hitler's, Professor Hitler's talk. And he gave a talk here in February. In continuous case, we have Wronski, and in discrete case, we have causality. The causality, in causality, the column is arranged by some shift. And, S is 0 and S1 is 1 here, and this is second column. And we need some notations tuned for n direction shift and height for m direction shift, and we also use tuned height. consistent around the curve. I don't think I need to explain more here because last week James just gave a talk on the ABS list, so we can jump. Okay. Because we will talk about the bilinear things. So the ABS list H1, 2, 3, and A1, A2, and Q. Okay. So once we have lattice equation, which is multidimensional consistent, or more strict condition CAC, and we can get Lux pair, and we can also get Bigland or double transformation. If your bar is, we consider it to be wave function, and this is Lux pair. And so in this way, we can call this double transformation because it is related Lux pair. And from this elementary curve, we can also consider many mirror transformations. James has a paper on this. Now in this part, I want to show how to get more solutions in conservative form for ABS list. We have a procedure to construct n solitons. The starting point is background solution using fixed point idea, and then we can get one soliton from Bigland transformation, and then we use Herta's perturbation expression, and we can find 2 solitons and 3 solitons, and from here, and we find the transformation and the conservative structures, and then we binarize the lattice equation, and finally to finish the conservative proof. So this is a way to get n-soliton solutions in constructive approach. In this way, we have got solutions for H1, 2, 3, and Q1. The question is, can we do some generalization in conservative form, and are they related, like in continuous case, by some limit procedure? The example is H1. I will take H1 as an example to talk about this. And this is H1 transformation and bilinear form, n-soliton solution, and causality entries. So in our proof, the starting point is a very concrete form of psi. So we start from such kind of psi, and then we try to find some shift formulas for f down tilt, down height, and up height. Such kind of shift formulas, and the relations we used is we find psi satisfies such kind of relations, and from here, and we can get some shift formulas for causality. But such kind of solutions can only be used to get those shift formulas with downshift. We cannot get upshift formulas. To get this, we have to introduce some auxiliary function. This is some trick. So this is psi, and the auxiliary function is phi. They are related by a factor, and the difference is this term and this term. So using such phi, because phi satisfies the shift relation, which is different from psi, and this is easy to get those formulas with up shift. But the entries for causality is phi, is not psi. So we have to do some other tricks to transform phi causality to psi causality using such relations. Now, what we want to do is, we have had Wronski solutions. We have had Wronski entries psi. And it is a very concrete form. And next, what we want to do is we try to find some conditions, and then we solve such kind of condition equation to find the new phi and psi. In this way, we can get some so-called new solutions. So this is somehow from functions to conditions. If gamma is, here we have coefficient matrix. If gamma is diagonal, in fact, we just get n solitons that we have got. But here, gamma can also be a general matrix. So in this way, we can get more solutions. So next question is to solve the causality condition consisting of such 4 equations. This is not difficult because we have had Toy-Bliss matrix. If we use Toy-Bliss matrix, and then we can get the general solution for phi for the generalized causality solutions. And now it is very similar as continuous case. In causality solutions, we can have a diagonal solution or Jordan block solutions, and they are related by some limit procedure. So, in other words, in terms of causality, we have Euro solution and a limit solution. And such generalization is okay for H1, H2, H3, and Q1. So in this case, in this way, we can get more solutions from solitons for discrete equations. I nearly finished my talk. And here are some questions of mine. And one question is, there are some non-autonomous lattice studied by Kajiwala and Alta and Satsuma and Willax. And it seems that the relation between autonomous and non-autonomous case are just, in autonomous case it's constant A, and in a non-autonomous case it's AN, and then A times N goes to summation of AN, and the power is a consecutive product. It's a symmetric change for B and N. So one conjecture is, can we do such non-optimalizations for ABS list or for Berliner case?
This is automatically in the ABS list
Yes.
already,
Yeah.
in the sense that the parameters can be thought of as functions of one variable, and that's still consistent around the cube. Therefore, the non-autonomous terms are already embedded in the list.
And the solution and the relation is in this way. I think so, maybe.
All I can say is that the A's and the B's, or the corresponding P's and Q's in the list, functions of one variable.
Yes, yes.
I don't
Function
know
of
if
one
that
variable, yes.
responds to your notation.
Yeah. So, yes, we don't want to get new solutions, our non-autonomous ABS list, but maybe we have known the solution, what solution are in this way. Another question is the Bigland transformation. From some, also there are many stories related Bigland transformation and lattice equations. In general, or for some equation, for example, the KdV and its superposition formula is very clean without any derivatives, and then such superposition formula can be a lattice equation in discrete case. And if there are some derivatives in the superposition formula, and then it is semi-discrete equations. I want to calculate some limit solution from the superposition formula of KdV. So this is a superposition formula of KdV, and also it is H1, and I want to get limit solution of KdV, so I take the limit K2 times K1, and then we get W11, and it is a solution of a potential KdV, and by and if we take a derivative with respect to x, and it is a solution of KdV. So for this equation, if we consider K1 to be T, and then we can get such semi-discrete equation. So that means we start from a lattice equation and we come back to a semi-discrete equation. We can do this further, and this is 3 solitons derived from the superposition formula. We just use the superposition formula twice, and then we can get 3 solitons. And then we take limits K3 times to K1, and then 2, and then K1, and we also get a limit solution, W111. It is a limit solution of KdV. And if same way, K1 is T, and we can get a semi-discrete lattice, semi-discrete condition equations. So can we get more, or it is integrable? Because for any multi-dimensional consistent lattice, we can do them in this way. We can start from multi-dimensional consistent lattice and then back to some semi-discrete case. That's how I finish.
Any questions?
Have you written down some of these? Can you write down what they look like? Because you have derivatives of the one soliton with respect to the spectral parameter on which it depends. In these formulae.
So maybe we can look at.
Do you have an example? I mean, a function of n and m, or something like this.
No, I don't know. In this case, which is n and which is m. I'm sorry.
I think he is asking that since you know the solution, you can actually calculate this derivative.
Therefore, you have a solution of the last equation. You have
Oh.
constructed the solution.
No,
From the
no, I don't think so.
Why not?
Because from here, W0 is independent of K. So that means here it is independent of K. Or it is independent of T here.
W1 will be dependent.
So that means
W1,
in your letter, you write the equation down, every Wn depend on T, right?
Yes, from here it is, yeah.
Yes, and how you relate it to the top equation? What is W naught in the lower equation? It's probably
I don't
Wn
think
minus
it is
1.
a problem because
How are these two equations related?
no, okay. We can look at the relation between H1 and the superposition formula of K-Dewey. And in fact, from here, it is W0 is also independent of K. Independent of K. But here, it is related to K.
Right. So no, I understand how you arrive to the third line, but how from third line you arrive to the fourth line?
This?
Yes.
Yeah, okay.
What is Wn minus 1? Is W naught?
Yeah. It's W. Yes, we give a downshift
But
of
that
this
doesn't
one.
depend on T.
Yes, for example, W0, no, minus 1. 0, 1.
And 1 does not depend on T. Or minus 1 doesn't depend on T.
No, all of them depend on T.
No, you say W naught does not depend on K. So it means
Yes.
Wn minus 1 doesn't depend on T.
No, I don't think it is a problem because
this was only the
Yes.
solution, W0. If you take this to be a solution of, then it's only a constant. Therefore, you cannot go that. But in the general form, yes. So the solution
Yes.
doesn't work for this particular solution, but it should work in general.
we just look at it is some relation. No, I don't know this is whether it
So the
is.
question is that you don't know any solutions
I
from
don't know.
to the last equation, even if you know some solutions to the.
No, they are not related. I don't think they are related. And for this one, maybe W is T square is a solution.
So the question